assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
This question asks us to consider this generic reaction where A goes to B and C, and it asks us to find the equilibrium concentrations of A, B, and C for three different values of Kc, or the equilibrium constant with respect to C, or the concentration. And it asks us to assume that the initial concentration of A is 1 molar and that there's no product. And yeah, so let's begin. We can express the equilibrium concentrations with equations. So let's say that A loses some amount. The change is going to be negative. We're going to lose A, and we're going to generate B and C. So we're going to gain some amount of B and C. The magnitude of this change depends on the stoichiometry of this reaction. There is no term in front of these values, so it's a 1-to-1-to-1 ratio of A to B to C. So if this is negative x, this is positive x, and this is positive x. And then equilibrium is the difference between the initial and the change, so that'd be 1 minus x, and then 0 plus x is x, 0 plus x is x. Great, and here's the equilibrium constant equation, concentration of B times concentration of C, no exponents, so there's an exponent of 1 that I haven't shown because these don't have terms in front, divided by the concentration of the reactants, which is also has no exponent because, or has an exponent of 1 because there's no term in front of A here. So we can then plug in each of these short little equations we generated for the equilibrium constants. This would be equal to x times x over 1 minus x. Great. And Kc is what's changing in each of these parts. So in A, Kc is equal to 1. B, Kc is equal to 0.01, and in C, Kc is equal to 1 times 10 to the negative fifth. And so we're going to have to find the equilibrium concentrations for these three chemicals under these different equilibrium constants. And just intuitively, since Kc is the concentration of products over reactants, as this number gets smaller, the amount of reactant should be increasing. The denominator should be getting bigger because this fraction is getting smaller. So we expect that this should go up as we go down here. I'm not going to work these out, of course, to take a lot of time, but the only thing you're changing is Kc here. So if you plug in a 1 here, you can then get the quadratic formula from this by rearranging some terms, and then you can solve the quadratic for x, and we can plug x back into each of these. So I'll say that for this first one, x equals 0.62. For this next one, again, same exact thing, plug in 0.01, rearrange your terms, get the quadratic, solve the quadratic, you get x equals 0.095. And then for this one, you get x equals 0.0032. Again, that's just plugging in Kc here, solving for x by solving the quadratic equation. So now let's plug these x's all back into here. I'm going to kind of block this off, and I'm going to put the concentrations for A right here and move down the line. And so if you do 1 minus 0.62, this would be 0.38 molar. 1 minus 0.095 is about 0.9 molar, rounding a little bit, and 1 minus this comes out, if you round it, just about to 1, doesn't really change. Like we expected, as Kc gets smaller, this fraction gets smaller, denominator gets bigger, so the concentration of the reactants is increasing. That's exactly what we see. And then each of these terms is just x. This is just 0.62 molar. This is 0.095 molar. And as you expect, if reactants are increasing in concentration, as we decrease Kc, the products are going down. And this is 3.2 inside. We're writing this in scientific notation, times 10 to the negative third molar, and same over here. Times 10 to the negative third molar. So these values here are the equilibrium concentrations for A, B, and C, given different equilibrium constants.